At first glance, the Eurofighter Typhoon presents a silhouette that seems almost anachronistic, a geometrical exercise in triangles and sharp angles that harkens back to the rigorous slide rule aesthetics of the late Cold War, rather than the smoothed, organic blobs of the fifth-generation stealth era. Yet to dismiss this machine as merely a loud, triangular relic is to fundamentally misunderstand the terrifying kinetic potential stored within its carbon fiber skin. It stands as a contradiction in aerospace engineering, a platform designed by a committee of nations that usually cannot agree on the definition of cheese, yet somehow managed to produce an air superiority fighter that defies the very laws of aerodynamics it relies upon. The delta wing configuration, historically known for bleeding speed in turns like a hemophiliac, has been manipulated here into a mechanism of violent agility, creating an aircraft that is inherently unstable, a beast that wants to flip over backward at every moment of its existence, only prevented from doing so by a quadruplex digital flight control system that makes thousands of micro-corrections per second. This is not a plane that flies. It is a plane that is continuously argued into the sky by its computers. The visual deception is potent. Where one sees a rigid delta, the pilot feels a weapon that can point its nose independent of its flight path, snapping into high angle of attack maneuvers that would tear a conventional airframe into expensive confetti. To understand the Typhoon, one must look past the Euro-canard cliches and into the sheer density of engineering compromise and brilliance that allows it to remain an apex predator in a sky increasingly populated by ghosts. The genesis of the Typhoon lies in the deep anxieties of the 1980s, a time when the Soviet flanker and fulcrum families were redefining what maneuverability meant, prompting a consortium of the United Kingdom, Germany, Italy, and Spain to embark on a journey that would be fraught with political indecision, budget wars, and the departure of the French, who took their ball and went home to build the Rafale. The resulting aircraft is a testament to the concept of relaxed static stability, a deliberate design choice where the center of pressure is placed forward of the center of gravity, making the aircraft aerodynamically divergent. In layman's terms, if the flight computers were to fail simultaneously, a statistical improbability bordering on the divine, the Typhoon would not glide. It would violently depart controlled flight in a manner best described as tumbling laundry. This instability is the key to its agility, providing the control surfaces with an abundance of authority that allows for instantaneous pitch changes. The foreplanes, or canards, located just below the cockpit, are not merely trim devices, but are active control surfaces that manipulate the airflow over the main delta wing, energizing vortices and delaying the stall at high angles of attack. This allows the Typhoon to perform a carefree handling routine where the pilot can yank the stick to the stops without fear of departing the flight envelope, assuming the aircraft doesn't simply decide to accelerate vertically while doing so. Before we descend further into the labyrinth of avionics and the specifics of the EJ200 turbofans that power this kinetic sculpture, if you appreciate deep technical dives into the machinery that defines modern warfare, I highly recommend you subscribe to the channel now to ensure you don't miss the upcoming analysis on the future of air combat systems. The propulsion system of the Typhoon is arguably its crowning glory, centered around a pair of Eurojet EJ200 engines, which are masterpieces of thermodynamic efficiency and brute force. These are not merely engines. They are controlled explosions funneled through a converging, diverging nozzle. Each engine produces 13,500 pounds of thrust dry and over 20,000 pounds with afterburner, but raw numbers fail to capture the responsiveness of the unit. The EJ200 utilizes a 3-stage low-pressure compressor and a 5-stage high-pressure compressor featuring bladed discs, or blisks, where the blades and the disc are a single piece of titanium alloy, reducing weight and increasing strength, but making maintenance a nightmare that requires replacing the entire stage if a single blade is damaged. A joyful prospect for ground crews. The thrust-to-weight ratio of the Typhoon, depending on fuel load and armament, sits comfortably above 1.15 to 1, allowing it to accelerate vertically. This capability is not just for airshow vanity. It grants the aircraft the ability to dictate the energy state of an engagement, recovering speed faster than nearly any adversary after a high G turn. Furthermore, the engines allow for supercruise, the ability to fly at supersonic speeds around Mach 1.2 to 1.5 without the use of afterburners. This is a critical tactical advantage, allowing the Typhoon to transit large distances quickly without guzzling fuel at the horrific rate of full reheat, keeping the thermal signature lower than an adversary screaming along in full burner. The digital engine control unit handles the complex fuel metering and nozzle geometry, allowing the pilot to slam the throttles from idle to full reheat in less than 4 seconds without the engine stalling, surging, or turning itself into molten slag, a feat that in previous generations required a delicate touch and a prayer. Structurally, the Typhoon is less metal and more chemistry set. Approximately 82% of the airframe surface consists of carbon fiber composites with glass fiber reinforced plastics, aluminum lithium, and titanium making up the rest. The extensive use of composites is not merely for weight reduction. It is integral to the aircraft's stealth features, or rather, its low observability features, as the consortium is careful not to claim full stealth. The carbon fiber skin is manufactured using laser projection to align the weave precisely, ensuring structural integrity under the massive torsional loads of 9G maneuvers. The wing skins are bonded to the spars, creating a rigid integral fuel tank structure that is incredibly stiff. Titanium is used in the canards and the outboard flaperons, as well as the engine bay heat shields, processed using superplastic forming and diffusion bonding, a manufacturing technique that sounds like something from a science fiction novel, but essentially involves heating titanium until it behaves like chewing gum, and then blowing it into a mold with inert gas. This construction method reduces the radar cross-section significantly compared to a metal aircraft of similar size, particularly from the frontal aspect. The S-shaped intake ducts shield the engine compressor faces, one of the biggest radar reflectors on a jet, from direct line of sight, although the Typhoon lacks the internal weapons bays of a true fifth-generation fighter. This leads to the external carriage of weapons, which inevitably spikes the radar cross-section, a trade-off the designers accepted in favor of payload capacity and kinematic performance. The aircraft relies on speed and electronic warfare to survive rather than invisibility, a philosophy that says it is better to be a hard target moving at Mach 2 than a ghost that becomes a sitting duck once detected. The Avionics suite, specifically the radar, has been the subject of a modernization saga so protracted and bureaucratic it deserves its own tragedy play. For years, the Typhoon operated with the Captor-M, a mechanically scanned pulse Doppler radar. While technically obsolete in the age of active electronically scanned arrays, the Captor-M was arguably the finest mechanical radar ever built, boasting detection ranges that embarrassed many early electronically scanned arrays. However, the future is the Captor-E, or E-scan, an electronically scanned array radar that introduces a unique swash plate repositioner. Unlike fixed-plate electronically scanned array radars found on American fighters like the F-35 or F-22, which have a limited field of view, the Typhoon's antenna is mounted on a movable joint, allowing it to be mechanically steered to look almost sideways while maintaining the electronic scan speed and agility. This gives the Typhoon a wide field of regard, allowing the pilot to fire a missile at a target 90 degrees off the nose and then turn away, beaming, while still providing mid-course updates to the missile, keeping the aircraft safe from return fire. This mechanical-electronic hybrid solution is typical of the Typhoon, over-engineered, late to the party, but offering a capability that is technically superior in specific tactical scenarios. Complementing the radar is the Pirate system, Passive Infrared Airborne Track Equipment, an oddly pirate-themed acronym for a highly sophisticated sensor mounted on the port side of the windscreen. Pirate operates in two bands, 3 to 5 microns and 8 to 11 microns, allowing it to detect the frictional heat of an enemy aircraft's skin at ranges exceeding 50 kilometers without emitting a single electron of radar energy. It acts as a clandestine search and track system, allowing the Typhoon to stalk stealth aircraft that are optimized to defeat radar, but cannot hide their thermal signature. The pilot interface is a study in information overload management, utilizing a glass cockpit dominated by 3 multifunction head-down displays. But the real magic happens in the helmet. The Striker 2 helmet-mounted display projects all critical flight and tactical data directly onto the pilot's visor. It is effectively a wearable heads-up display. The system tracks the pilot's head position with optical sensors, allowing them to designate targets simply by looking at them and pressing a button on the hands-on throttle and stick controller. The helmet also integrates night vision directly into the digital feed, eliminating the need for heavy, neck-breaking night vision goggles. The voice control system, known as voice throttle and stick, allows the pilot to execute non-critical commands by speaking to the aircraft. While this sounds futuristic, in practice it requires a disciplined cadence, and there is something inherently dry about a British pilot asking their plane to select AMRAAM in a calm voice while pulling 7 Gs. The cockpit is designed to facilitate the sensor fusion concept, where data from the radar, Pirate, and the formidable defensive aid subsystem is combined into a single tactical picture. The defensive aid subsystem, named Praetorian, is arguably one of the most comprehensive electronic warfare suites in the world, housed in wingtip pods that look like afterthoughts, but contain antennas for electronic support measures, missile approach warners, and towed radar decoys. The towed decoy is a particularly clever piece of kit. It is a small transmitter trailed behind the aircraft on a Kevlar cable, broadcasting a signal that seduces incoming radar-guided missiles into attacking the decoy instead of the jet, a sacrificial lamb for the electronic age. Now, as we balance the scales between the raw kinematic power of the Typhoon and the stealth-centric philosophy of its competitors, I want to pause and ask you a question for the comments. In a hypothetical engagement between a fully loaded Typhoon and a stealth platform like the F-35, do you believe the Typhoon's superior speed, altitude, and missile kinematics can overcome the stealth advantage, or is the first look, first shot dominance of stealth insurmountable? Let me know your thoughts and reasoning below. The weapon systems integrated into the Typhoon turn it from a sports car into a sniper. The crown jewel of its arsenal is the MBDA Meteor, a beyond visual range air-to-air missile that fundamentally alters the geometry of aerial combat. Unlike traditional solid rocket motors that burn out in seconds and leave the missile coasting and decelerating toward the target, the Meteor utilizes a throttleable ducted rocket, essentially a ramjet. This allows the missile to manage its fuel, cruising efficiently to the target area and then throttling up to Mach 4+ in the terminal phase. This creates a no-escape zone 3 times larger than that of the American AMRAAM. When a Typhoon launches a Meteor from 45,000 feet at Mach 1.5, it imparts a massive kinematic energy boost to the weapon. The combination of the Typhoon's high-altitude performance and the Meteor's propulsion means the Eurofighter can engage targets from ranges where the return fire simply runs out of energy before it can reach. For close-in combat, the Typhoon carries the advanced short-range air-to-air missile, which, despite its name, has a longer range than the Sidewinder and can be locked onto a target over the pilot's shoulder using the helmet sight. In the air-to-ground role, the integration of the Brimstone missile and the Storm Shadow cruise missile provides a swing roll capability. The Brimstone, originally designed to destroy massed formations of Soviet tanks, uses a millimeter-wave radar seeker to find targets autonomously, while the Storm Shadow allows the Typhoon to strike hardened bunkers from hundreds of kilometers away. The sheer variety of ordnance requires a robust hardpoint layout, The Typhoon features 13 hardpoints, allowing for a mix of fuel tanks, missiles, and targeting pods that creates a drag profile resembling a flying brick wall, yet the EJ-200s push through it with indifference. Comparing the Typhoon to its contemporaries, the Rafale and the Gripen, reveals distinct national philosophies. The French Rafale is a masterpiece of omni-role capability, designed from the outset for carrier operations, resulting in a robust landing gear and superior low-speed handling, but slightly lower thrust-to-weight ratio compared to the Typhoon. The Gripen is the budget-conscious guerrilla fighter, designed to operate from snowy roads and be serviced by conscripts. The Typhoon, however, was born as a purebred interceptor, an air superiority machine first and a mud mover second. Its wing loading and thrust capability are optimized for high-speed, high-altitude energy fighting. Against the Russian Su-35, the Typhoon lacks the thrust vectoring nozzles that allow the flanker to perform the physics-defying Cobra maneuver. But Western doctrine generally views such maneuvers as a great way to lose all your airspeed and become a stationary target. The Typhoon pilot would likely prefer to keep the energy high, utilizing the superior climb rate to attack from above. Against the F-22 Raptor, the Typhoon is at a distinct disadvantage in detection range due to the Raptor's extreme stealth. But in a merge, a visual range dogfight, the Typhoon is one of the few aircraft that can arguably hold its own against the Raptor, provided the pilot can manage the tremendous G-forces. The G-suit used in the Typhoon is a full-body hydrostatic garment, necessary because the onset of G-force in this aircraft is so rapid that standard gravity suits cannot inflate fast enough to stop the blood draining from the pilot's brain. Modernization of the Typhoon is not merely about bolting on new weapons. It is about a fundamental shift in the aircraft's digital architecture. The long-term evolution plan aims to keep the airframe relevant into the 2040s and beyond, bridging the gap to the Future Combat Air System and the Global Combat Air Program. This involves a complete overhaul of the mission computer system, replacing the distributed processor architecture with high-speed avionics that can handle the massive data throughput of the E-scan radar and future electronic warfare threats. Aerodynamically, the aerodynamic modification kit has been tested, featuring fuselage strakes and leading-edge root extensions that increase the maximum lift by 25%, improving the turn rate and nose-pointing authority even further. This is a classic example of European engineering, taking an already unstable aircraft and bolting on more surfaces to make the airflow even more complex. There is also the integration of the Lightning 5 targeting pod, providing high-definition imagery for ground attack, turning the interceptor into a precision bomber. The Eurofighter Consortium is also exploring the possibility of manned-unmanned teaming, where the Typhoon would act as a mothership controlling a swarm of loyal wingman drones. This requires not just software updates, but a philosophical shift in how the pilot operates the machine, from a stick and rudder flyer to a tactical battle manager. The manufacturing process of the Typhoon is a logistical ballet that reflects its multinational origins. The wings are built in Italy and Spain, the fuselage sections in Germany and the United Kingdom, and the final assembly takes place in all 4 partner nations. This distributed production line was designed to share employment and technology transfer, but it also means that parts of the aircraft travel more miles on trucks and transport planes before assembly than some aircraft fly in their entire operational lives. Despite this, the tolerances achieved are microscopic. The mating of the fuselage sections uses laser tracking to ensure alignment within fractions of a millimeter. The sheer cost of the program has been a perennial punching bag for critics, with the unit cost fluctuating wildly depending on how you calculate development expenses, but generally landing in the territory of astronomical. However, the result is an ecosystem of aerospace capability that has kept the European defense industry alive. The Typhoon has found export success in Austria, Saudi Arabia, Oman, Kuwait, and Qatar, proving that despite the high price tag and the complexity, nations still value raw kinetic performance. The Tranche system of upgrades means that a Tranche 1 aircraft is a very different beast from a Tranche 4, with the early models being essentially pure air-to-air fighters, and the later models being fully mature multi-role platforms. Buying a used Typhoon is not like buying a used Honda. The compatibility of spare parts between tranches can be a logistical headache that requires a PhD in supply chain management to decipher. In operational conditions, the Typhoon has seen combat over Libya and in the counter-ISIS operations in Syria and Iraq. These missions, primarily air-to-ground, proved the platform's versatility, but also highlighted the limitations of using a thoroughbred racehorse to pull a plow. The Typhoon performed admirably, delivering pave-way bombs and brimstone missiles with precision. But the wear and tear on an airframe designed for high-G dogfighting when subjected to long-endurance loitering missions is a factor that maintenance crews monitor closely. The environmental control system, designed to cool the avionics and the pilot, works overtime in the desert heat, and the sand ingestion is a constant threat to the delicate blisks of the EJ-200s. Yet the reliability has been surprisingly high for such a complex machine. The maintainability was a key design requirement, with built-in test equipment that can diagnose faults down to the specific circuit board. Of course, diagnose is one thing. Accessing a component buried deep within the fuselage through a panel the size of a toaster requires a mechanic with the flexibility of a gymnast and the patience of a saint. The landing gear is robust enough for rough landings, but lacks the reinforced catapult bar of naval fighters, meaning the Typhoon will effectively never fly from a carrier, limiting its strategic projection to land bases. This limitation is often cited by proponents of the Rafale, but for nations with fixed borders to defend, the Typhoon's intercept capability is paramount. As we look at the legacy of the Eurofighter Typhoon, it stands as a symbol of what can be achieved when nations stop fighting each other and start fighting physics together. It is a machine of extremes, extremely fast, extremely agile, and extremely expensive. It represents the pinnacle of fourth-generation fighter design, pushing the boundaries of what is possible without a clean-sheet stealth design. It is likely the last manned fighter designed and built solely by this specific consortium of nations, as the future shifts towards sixth-generation systems that may look very different. The Typhoon proves that aerodynamics is not just about smooth lines. It is about brute force applied with surgical precision. It remains one of the few aircraft in the world that can supercruise at 50,000 feet, detect a target 100 miles away, and then turn inside a phone booth if the fight gets close. It is a technological marvel that somehow emerged from a bureaucratic nightmare, a diamond forged in the pressure of international politics. It is maneuverable not just in the air, but in the market, adapting to new roles and threats decades after its initial conception. If you enjoyed this detailed breakdown and want to help the algorithm identify high-quality aerospace content, please hit the like button. It supports the channel and ensures we can keep bringing you these deep dive analyses. Until next time, keep your eyes on the skies.